in a series on igneous rocks and volcanoes. In this video, we'll be discussing the Bowen's reaction series and differentiation of different types of igneous compositions. As we mentioned in previous videos, we discussed the geologists classify igneous rocks based on both the texture or the size of the individual crystals and the composition, which is what the igneous rock is made of. These are the basic compositions and textures as laid out in this chart. We have textures ranging from ultramafic to felsic, and it's all based on the amount of silica in the rock, the relative amount of silica, where felsic has the most silica and ultramafic has the least. Now, our Earth's mantle is most like the ultramafic composition. So why is it that on our thin crust that's surrounding the mantle do we have variations in this composition? Why isn't all of our crust just ultramafic? How do we get a felsic magma? And so that's what this video is going to try to explain. And why are the continental plates felsic and intermediate and the ocean plates mafic, right? Where we have decompression, melting, and we're creating new oceanic plate at the divergent plate boundaries, the mid-ocean ridges. We're constantly generating mafic type rocks, right? Whereas we have the flux melting, the generation of these volcanic arcs along the subduction zones. We're generating primarily intermediate and felsic type compositions. So why is it that we're making felsic and intermediate magmas there? It has a lot to do with the temperature at which different minerals crystallize, right? Think about the temperature at which ice crystallizes is 0 degrees Celsius, right? Begins to start to turn into ice. Water begins to turn into ice at 0 degrees Celsius. Well, different minerals crystallize at different temperatures. Quartz will go from magma to a solid crystal at a much different temperature than will ice, and it'll go from a solid to a liquid at a much different temperature than will olivine, right? So it's all about those different temperatures of crystallization and melting that allow for these different compositions. Basically, what it boils down to is some minerals will solidify and get left behind, while others stay in the magma and continue to move along. And it's essentially distillation of magma, where these, especially these convergent boundaries, are basically giant distillation areas for magma. So there are, I like to break it in 3 separate different ways, but they're fairly similar, and they're all based on this idea. Crystal settling, partial melting, and assimilation are 3 ways to create new compositions of magma. And here is a simplified version of the Bowen's reaction series, and this just shows the rough temperature of melting or crystallization and the different minerals. And here, very high melting temperatures, olivine, and a very low melting temperature, about 750 degrees Celsius, is quartz, right? And this is like the spectrum of these different minerals and the different melting temperatures. And of course, there's a variety of other factors at play, but for the sake of simplicity, let's just talk about temperature. And so which of these will crystallize first? And that would be the thing that takes the highest melting temperature, right? So olivine will crystallize first as things start to cool, and quartz will crystallize last because it has the lowest melting temperature. So as the magma cools down, these more mafic minerals, which are up here on our Bowen's reaction series, will crystallize first, and then you're left with a more felsic type composition where you have K-feldspar, muscovite, and quartz. So here's kind of the conceptualization of that. This is the first of those 3 different ways you can get different compositions, known as crystal settling, right? And this magma, these minerals that are starting to settle out of the magma, they are more mafic and they crystallize at a higher temperature. And those will slowly settle out over time, and your magma slowly becomes more and more felsic over time as a result, right? And then the partial melting is almost the same idea, except you're starting to melt something. And what's going to melt first? The temperatures with the lowest melting temperature, the more felsic type minerals with that lower melting temperature are going to melt first. So here you start to heat up the rock and you start to melt out the felsic stuff first, leaving behind the more mafic rock. That's another way you can change the composition. And then finally, the last way that you can change the composition is bringing in rocks of other chemistries and melting those and incorporating those into your magma chamber. And this is much more common at the more crustal type processes closer to the Earth's surface, where as the pluton moves through the host rock, it's incorporating part of that host rock with it. And so you can form these different magmas based on these different concepts, right? You can get start out with a fairly mafic magma, and as it moves through the crust, it can be distilled through this crystal settling, through this partial melting processes to become more and more felsic over time, right? And that brings us to the section on volcanic hazards, which we'll discuss in the next video. Thank you all for listening. Hopefully I was able to distill this down for you in a way that's comprehensible. And if you have any questions, please feel free to put them in the comments and hopefully I can address them. Thanks a lot.